Ladies and gentlemen, this time in the SEAM studio, in the helicopter series, we're looking at the lift formula and the energies involved. And I think, you know, it's one of the places where we must make sure that we understand the lift formula. And it's slightly different from the aircraft. As I say here, the lift formula is the same found as in a fixed wing. However, the application is slightly different. There are more variables in it, and we're going to go through all of them. It's important to understand in terms of the energies. That's the lift part, the energies part, energy transfer, energy priorities, energy containment, energy rate of usage. One of the biggest problems that we've got in helicopter flying is that somehow people think that the energy will always be there, and they don't understand that you actually can run out of energy. And how do you work with the different energies? How do they interface? And how is energy manipulated or transferred in the one form to another form? And not that big series, so just hang in there. First of all, we're looking at the helicopter lift formula, the breakdown. Straightforward. Here we've got lift equals coefficient of lift half rho v squared s. And straight away, I'm going to change it slightly by saying, remember that in a fixed wing, the speed is only translational, all right, and then there is an angle of attack. Now in this case I can't call it an angle of attack because it will be a disk change. We'll get to that. So let's just say from a conventional point of view, from a helicopter point of view, we've got now extra, because remember the blades are also rotating, and therefore there's rotational energy as well. It's like a fixed wing. Well, that's right, a fixed wing. This is a rotary wing, and the rotary wing also creates a flow. In other words, we can lift off straight into the hover. That is still flying, and for that you need lift, or if you then wish, thrust. All right, so how do we manipulate up and down? Obviously, we've got the collective pitch changes that we can do. So just to have a look at the formula, lift equals coefficient of lift half rho v squared s, and all of a sudden there are two things. Now normally on the ground, when we start up, we would use the engine to excite the rotation of the blades. Once the rotation is done, you can get airborne simply by increasing the collective pitch, because that is the collectiveness of the pitch of both blades. So just on the helicopter here, in other words, the pitch changes on both sides and then collectively, so the whole disc is creating more lift, and then when we go forward we start talking about thrust. All right, so that is the main thing here that we've got to look after. The next one, just a little bit more in there, the rotation is the main rotor RPM. The main rotor RPM. And normally the main rotor RPM must stay a constant. All right, in this case it must turn around this way. This must stay a constant, driven by the engine, the main rotor RPM, a constant. And remember, it is mechanically onto the tail rotor, and the tail rotor RPM is therefore a direct function of the main rotor RPM. It's geared in a relationship, 4 to 1, 5 to 1, whatever the case might be. All right, the translational lift on the other side is flow over the disc. So if you now, let me just get hold of the helicopter with a serious disc here. If you now look, I've got this R44 with a huge disc. Remember that the flow is over the disc, and you must see this whole disc maybe not as a solid wing, but as a part that is functioning as one and not necessarily independent now. All right, because this disc can change the disc attitude. You can manipulate obviously through the cyclic pitch. All right, So the thing that we are looking at on the other side is we set the blade angle of attack through the collective pitch. That is fine. And then at the bottom saying that through the cyclic you can actually change the angle again. So if you come in and you change this, remember from here in forward flight, let's have a look, then we'll see the wind is coming from here. Now let's keep the wind a constant, and you'll see if you manipulate the disc, the wind actually comes from a different side, and that changes the angle of attack quite dramatically. So we have to look at, you know, how to fix and manipulate that one. All right. On the next one, I say here, we've now got energy. So we get energy from the engine. And we have put that energy primarily into the rotational side. But we are still not flying. The collective pitch is the angle of attack, but the angle of attack of what? Of the energy mediator, intermediate or intermediary. All right. Remember that the form and shape of the blades, or the form and shape of the wing, that pretty much stays a constant in our argument, but the rotational speed will obviously change. So the S part is the size and the shape and the form of the actual blades. So that is sort of the middle ground through which things are happening. And this is the energy manipulator. It is the collective pitch. What is it doing? If you increase the pitch, you actually increasing the torque demand. The engine puts in more fuel and it stays there, and now it starts creating the lifting force as required. Great. At the bottom here, translational, we said you can now, if you get into the hover and there's more power available, now you can start going forwards. And once you've got the flow over the disc, and this is one thing that I think that we must just be very careful to understand. Flow over the disc, in other words, forward speed, or if you're standing still and there's a high wind velocity from the front. But let's say now, for now, there's no wind, so we sit in the hover and we've got to move forward, and that creates a flow over the disc. That is just immensely powerful. You'll see later on that its angle of attack, if you put too much on and you're trying to hover and the main rotor RPM comes down, the one way of stopping that is actually to get forward speed, because the disc, when you energize it through forward speed, is just absolutely amazing. Right, I now have a look here. The disc changes, cyclic changes. The disc, in other words, its relationship to the relative airflow. And although we can now talk about an attitude change, it is not something we can say. It will definitely change the angle of attack on the physical blades. So I could have said there that through the disc changes we're changing the angle of attack because the relative airflow strikes it at it from a direction where the angle of attack is increased. Then helicopter, if we carry on here, what I've brought into now is the energies at play. Now I've already mentioned the power, so that is power or thrust. Now it depends, you can even call it lift if you wish, but remember the power must first start swinging the blades. Then once it has now sped it up to the speed that you wanted and you increase the angle of attack, the moment that you start doing that, there's definitely a huge increase in drag and more power will have to put in to maintain this. Okay? And now, once we have lifted off and we start forward flying, then it's like a propeller. Then you have got your forward thrust. So let's just have a look at that. So that's the main thing. The power must come in. What happens with the power? Well, first of all, we get the power into rotational speed. In other words, in this one here. Let's see if I haven't got that. Yes, I've got that there. I say that rotational is then primary demand, and then if there's excess power, then we can put it into height or forward flight or both. And you'll say to me, how is that possible? You've got to get into the hover to go forward. No, you can do a skid off, or you can do a roll-off landing. There's helicopters with wheels, so that's not a problem. So they can roll on the ground until they have sighted the disc, and they make use of translational lift to get airborne if you're slightly heavier. Bigger helicopters, hover takeoffs, you don't necessarily do it unless the area is not suitable. Otherwise, it's a good thing to do a roll-off, if you wish. Okay. Up to you. How are you going to use it? So that's the primary function. Then, if I look at the energy transfers, now this is where I need you just to start thinking that you've got the three energies. Remember, we said that we've got the mechanical energy, and the first thing that we do is we put the mechanical energy to work, and it starts spinning the blades. Once the blades is up to speed, it will demand a certain amount of power to maintain the rotational velocity. If you now start increasing the collective for the helicopter to lift up, the demand for power will dramatically increase. All right? So the first thing that we do is we say mechanical energy is required to overcome the drag, to spool up, and that is for the main and the tail rotor. Right, now we've got that. Once rotational energy has been achieved, additional power can now be expended for height into the hover. At this stage, let's just stick with the hover and then the forward flight. So should further power be available, sometimes you get in the hover and say, I haven't got that extra little bit of power to go through transition, and I cannot do a roll-off. In other words, I simply cannot fly the helicopter. So let's just work with that scenario for now. Then should further power be available, it is now transferred into translational energy. And that is where we say, from the point where we start flying forward, at stationary flight, then there's a transition period until we are translating. Translating just means to move forward. Okay, but and the term that you're going to choose is transition. It's the phase between stationary flight and, let's call it, where the aircraft doesn't really know what's happening, and there's a little bit of shaking and moving. And here, from about 12 knots and up, you are what we call through the transitional phase. Okay? And then we're talking about translation or just normal forward speed, which will obviously influence how well the disc can support you. Now, after achieving minimum speed requirements and more energy is needed, then we put the extra into height. Whoa! So you've got to get this one. We start off by we're spooling up the engine. Now, when it's spooled up and it's fine, it's got spare, we take it off into the air. If there's no spare, we accelerate, and you will see in the curves that you always accelerate to 40 knots, and from there on you will then get 50 feet above the ground, and then you accelerate again to your VY, velocity, your best climbing speed, and then obviously you climb away. So it's pretty much a sequential usage of the power. Oh yes, we can go directly in and do other funny stuff, but remember, we're now with the basics. In other words, spool up, forward, and then climb. And each section needs extra energy. So height, as you're attaining it, is actually your vault. Not for money, but for kinetic energy. Because that is where you store the energy, because height has got the potential to turn into kinetic energy or speed. And that is why height becomes such a valuable item in the bag. Right, reducing the energy input from the engine. So the energy input from the engine normally is you'll go slightly down on the collective, and if the engine is governed, the governor itself will make a change with the engine. If it's something that hasn't got a governor, you'll go down and slightly throttle down to maintain that. But then there are two energy sources. The first energy source is the aircraft has got forward speed. So with less power, now I didn't dump the power, I just went down a little bit on the power. I want to maintain the same height, then I'll have to increase the attitude slightly. In other words, to make use of the secondary part of the disc. And then what I'm going to pay here in exchange is the extra speed that I had. That speed is going to be exchanged, and it's going to stay at height now. And now everything will happen slower. Or if I want to maintain the speed a constant, that's fine. Then I just start descending by lowering the nose ever so slightly. And in other words, I'm using up of the potential energy. Energy power is removed completely. So let's say we take the energy completely away, then then you've only got potential energy. Now height, listen to this, height is now exchanged for rotational as well as translational requirements. So now we're sitting, the engine is taken away, and we cannot just go forward, we've got to go down. Relative airflow comes from the bottom, and that energy exchange must in two ways. First of all, we're going to reduce the angle of attack to a minimum to get the drag a minimum, and then it might be that the autorotator forces on here will make the blades to speed up higher than what its design is. And the only way that we can manipulate is just by increasing slightly more the drag, by putting a little bit more collective pitch. Well, that's good, because at the end of the day, the rate of descent must be stabilized as well, because sometimes this whole effort will have to stop before we get to the ground. And only energy and the usage of energy will sort that out. So you cannot run out of rotational, because then it's like having no wings. You're just going to simply fall out of the sky at 9.8 meters per second square. Or so this is not negotiable. Translation requirements is, remember, you can have your rotor option, but if you go straight down, then the disc itself is not properly energized. So you actually want forward speed. And you will learn later on that all helicopters, around about 70, 65, 60 knots is the autorotation speed. And normally you will have then flare effects, and you can manipulate flare until around about 40 knots. Below 40 knots, the flare effect is going to be minimal or none, depending on the design. So just think of that. So as you're coming down with a helicopter, you've got 65 knots, you can take 69 foot forward speed, and you can take it into a flare situation to break the vertical speed and the forward speed, because there's a rate of descent and there's a forward speed. Okay? You want to make both of those. So you take this energy and you put it in this energy, in other words, translational into rotational to stop. If you don't do that and you bleed your speed off here, then there is no more flare and flare effects that you can use, and at the end, at the bottom, you can only pull up the collective in order not to hit the ground. Okay. Sure. So the first one is rotational, and you actually want to maintain your speed. You don't want to bleed your speed. Drag must now be a minimum. Rotor RPM is controlled through the collective pitch, which is drag, and then speed is controlled by the attitude, and obviously you've got your stored energy. So if you descend steeper and faster, then you're using up the potential energy faster. That's why we've got speed. We say this, the best rate of descent here, let's say in the autorotative state, is 65 knots or 60 knots, well, 65 knots. Then we maintain 65. Theoretically speaking, if we descend higher than that, there's going to be other effects, and we will discuss that later on. So let's just work on a constant of, so at least with the speed and the drag that we've got to overcome at that moment in time, the rate of using the height up, because eventually there's going to be height left. Remember, this is a volt of energy, and the quicker you go down, the quicker you're using up the volt of energy. So high speed, not always a good idea. There's other things to slightly manipulate. But now, on the other hand, if you have got no flare effect left, you've got no more energy left, you've used up everything, then there's no more height to exchange. And the one thing that we must end at the end of the day, when we flare the aircraft close to the ground, there must be still this distance between the aircraft's tail and the ground, because, just listen to this, if this is the ground and you flare too late and you put the tail in, the speed at which you put the tail in is the speed of the accident. There's no other thing. The speed that you put the tail in is the speed of the accident. Not good, because after that it's going to cut off the tail and do funny things. So you will always want to be able to go to a height where you can maximize the flare, and then you can break this forward speeds and the rate of descent into something that the body can absorb. Here, it's probably sounding a bit frightening at this stage, but not so to worry about it. Speed or energy transfers. The third one I've got here is kinetic energy is transferred into rotational requirements during the flare. Now, this also reduces the rate of descent to whatever minima you can achieve. Main point is, if you've got no more potential energy, you've got nothing to exchange. So during the descent, we exchange the potential energy, all right, and we also maintain, we put that energy into forward speed, all right, as well as rotational speed. We maintain the rotational speed by manipulating the drag, and the speed by manipulating the attitude. And we maintain that. When we get to the ground, we'll take, first of all, that speed that we're doing there, and we can exchange it. And then you get to the flare and the flare effects. And there will be another presentation just about the flare and the flare effects. For now, remember, you need speed to do a flare. Zero speed, zero capability of a flare, therefore no effects. The final CP application, stored energy in the blades. So all that I said here is that as you would stop, you level off. Now there's no energy left, only the ones that is left in here. And that is what we're going to lose to the collective to do the final landing. Is it ideal? No, of course it's not ideal. I cannot say that it is ideal. We are definitely not yet busy with auto-rotation, but you also need to understand how energies are exchanged. It might be in the extreme form now, but if you've got your engine, then you can use very little engine. You can still use a rate your potential energy. It will go into speed. Speed can put into a flare effect, and so that's going to become part of your daily operations of your helicopter. The end result is, after the engine is shut down or lost or whatever, and the state of zero energy when everything comes to a halt. So once you're on the ground, that's it, end of story, fine, bang, no more energy left. We started with no energy, then we put fuel in which turned the engine, and the whole story goes up and the whole story comes down, and there's no more energies available to do anything with. So let's conclude. Understanding how energy is manipulated is the beginning of understanding power management in a helicopter, and you will see later on that power management in the helicopter will play a major role in your flight safety. Height, besides its safety value, because height gives you time to do things, must be seen as the storehouse of energy. I want to, right in the beginning of your careers, excite you to the point to say, it is very cool to fly very low. The lower you fly, the less chance you have of survival if anything goes wrong. Flying is a dynamic environment. So sometimes we have to fly very low by the very nature of the application of the helicopter. In other words, we will be scratching the lion. I understand that. But when it's not needed, remember that height, especially if you're ferrying from one place to another place and you do not need, sit higher. Height gives you time, it gives you energy in the bag, it gives you so many things, and you must just have it. Because if you don't have it while you've got your engine to get your money in the bag, height in the bag, it's going to be too late. All right. More about that in future presentations. The engine is the main supplier of energy, so that failed stored energy can be used, rotational and translational. During a flare, the translational energy can be transferred into rotational energy, which it does, and then you break all the speeds. Energy is transferred into, listen here, energy is transferred into momentum, and energy is required to reduce. Now the energies, you must know the energies. So what I'm saying is that we start from a stationary point. We use everything to move, it's got momentum, but we've got to reduce that as well. So there's an acceleration and there's also a deceleration. Everything comes to a standstill as well. Sometimes people think you don't need energy to go from a momentum position to a standstill. Well, in our case, you better use the embedded energies available to make sure that you don't stop 6 feet under the ground. All right. So that is then as far as we go. Just to say finally, really in the beginning, if you don't understand the usage of these things and you start practically flying the machine, it wouldn't make, let's call it, subconscious sense. The decision-making power is going to be less. So if you don't know, ask. And then we say it again, and we will explain it in another way. But at the end, you must understand that flying helicopters, you're going to become the controller of energies in various formats. And you must be able to exchange them in the correct manner so that I can see you next presentation.